Stars and snowflakes, schemas for analytics, has explored in Chapter 2. A wide range of different data models are used in the realm of transaction processing, depending on the needs of application. On the other hand, in analytics, there is much less diversity of data models. So there is much more diversity in data models in transaction processing than in analytics. Many data warehouses are used in a fairly formulaic style known as a star schema, also known as dimensional modeling. The example schema in Figure 3.9 shows a data warehouse that might be found at a grocery retailer. So this data model is what you would see at a typical grocery store. Example of a star schema for use in a data warehouse. At the center of the schema is so-called fact table. It is in this example it is called fact underscore sales. Each row of the table represents an event that occurred at a particular time. Here, each row represents a customer's purchase of a product. So this fact underscore table uh, is actually it's kind of like the star schema where each rows that the others are related to consists of a different table. So if we were analyzing website traffic rather than retail sales, each row might represent a page view or a click by a user. So this row might represent a page view or a click of a user if we're not analyzing a business, but they have the same access pattern. Usually, facts are captured as individual events because these allow maximum flexibility of analysis later. So these facts such as DM underscore date, DM underscore customer are captured using a different table because they allow for maximum flexibility of analysis later. So they essentially allow us to scan it more efficiently later. However, this means that fact table can become extremely large. A big enterprise like Apple, Walmart, or eBay may have tens of petabytes of transactions history in its data warehouse, most of which is in fact tables. So this data warehouse have a petabytes compared to a maximum of terabytes in a transactional database because it consists of different or combination of those transaction database. So it consists of a petabytes of transaction history in its data warehouse, most of which is in fact underscore tables. So most of which are there in its column and row. Some of the columns in the fact tables are attributes, such as the price at which the product was sold and the cost of buying it from supplier, allowing the profit margin to be calculated. So some of the columns in this fact table are attributes, such as the price at which the product was sold and the cost of buying it from the supplier, allowing the profit margin to be calculated. So some of these columns are, this analytic storage engine is actually column oriented storage. So these columns will be based, some of it will consist the actual price and the actual price that we sold it, therefore allow us to compute the profits. Other columns in the fact table are foreign key references to other tables called dimension tables. So other column reference to another table that we call dimension tables. As each row in the fact table represents an event, the dimension represent the who, what, where, when, how, and why of the event. So this dimension table that we reference uh, represent the who, what, where, when, how, and why of each of this row. So that's what the dimension table means. For example, in figure 3.9, one of the dimension is the product that was sold. Each row in the dim underscore product table here represent one type of product that is for sale, including its stock keeping unit SKU, description, and brand name, category, fat content, package size, etc. Each row in the fact underscore sales table uses a foreign key to indicate which product was sold in that particular transaction. So each row here represent which product were sold in this particular transaction of the product. For simplicity, if the customer buys several different products at once, they are represented as separate rows in the fact tables. So if you customer buy different products here, it will be represented as a different rows in this fact underscore sales table. Each row in the fact underscore sales table uses a foreign key to indicate which product was sold in that particular transaction. Uh, so if the customer buys several different products, they are represented in separate rows in the fact underscore fact table. Even date and time are often represented using dimension tables. So even date here, dim underscore date table are represented in another dimension. Because this allows additional information about dates, like metadata such as public holidays, to be encoded, allowing queries to differentiate between sales on holidays and non-holidays. So because the reason you would separate this is that it allows you for metadata that allows you to differentiate between sales on holidays and non-holidays. The name star schema comes from the fact that when the table relationships are visualized, the fact table is in the middle, surrounded by its dimension tables. So that's where the star schema came from. Because this is just like a data, of course, a 1010 in the actual data, but if you represented it in this table, this is how it looks like. That's why this analytic storage engine are based from star schema. So it's surrounded by its dimension tables. The connection to these tables are like the rays of a star. That's why it was called star schema. As you can see, it's like the ray of a star. A variation of this template is known as the snowflake schema, where dimensions are further broken down into subdimensions. So there's more nuance or another type that based from this schema is a snowflake, where these dimension are further broken down in subdimensions. For example, there could be separate tables for brands and product categories. So you could separate this table brand and categories if you want snowflakes. And each row in the dim underscore product table could reference the brand. So this product underscore table, each row of this could reference the brand and category as foreign keys rather than storing them as strings in the dim underscore product table. Snowflake schemas are more normalized than star schemas, but star schemas are often preferred because they are simpler for analysts to work with. So normalize meaning they are more consistent in synchronization than so it's not the norm it's less denormalized than the star schema, but star schema are still being preferred or currently being used practically by analysts because they are simpler. In a typical data warehouse, tables are often very wide. Fact tables often have 100 columns, sometimes several hundred. So in a typical data warehouse, each of these tables are often very wide, and fact tables, which is the middle, is have over 100 columns, sometimes several hundred. So that's the usual because it's a column oriented database and it's a combination of multiple OLAP. Oh well, yeah, sorry, multiple transaction storage engine. Therefore, it's a lot and it a lot of dimension table reference to it like a star schema. Dimension tables can also be very wide as they include all the metadata that may be relevant for analysis. For example, the dim underscore store table may include details of which services are offered at each store. So this dim underscore store may include all the services. Therefore, this may contain, they contain a lot of columns as well. So they are very wide, which whether it has an in-store bakery, the square footage, the date when the store was first opened, and when it was last remodeled, how far it was, or it is from the nearest highway, etc. So those are the columns that you could add to have further more nuanced queries that allows you to make better business decisions. Column-oriented storage. If you have trillions of rows and petabytes of data in your fact tables, so again, that's trillions of rows and petabytes of data, unlike the maximum like terabyte for each transaction storage engine. Storing and querying them efficiently becomes a challenging problem. Dimensions tables are usually much smaller, like millions of rows. So in this section, we will concentrate primarily on storage of facts. So how do we store those trillions of rows compared to millions, such as dimensions table? So imagine if dimension table has millions and we have trillions in fact tables. Therefore, we definitely have multiple or a lot of dimension table around our fact underscores table. Although fact tables are often over 100 columns wide, a typical data warehouse query only accesses 4 or 5 of them at one time. Select asterisk queries are rarely needed for analytics. Take the query in example 3.1. It accesses a large number of rows. Every occurrence of someone buying fruit or candy during the 2013 calendar year, but it only needs to access 3 columns of the fact underscore sales table, date underscore key, product underscore sk, and quantity. So this large number of rows that contains like trillions in our fact tables is the occurrence of someone buying fruit or candy during 2013 calendar year. So you could imagine that's the event we discussed in the star schema. But it only needs to access three columns of the fact underscore sales table: date underscore key, product underscore SK, and quantity. Here, product and the quantity. So those three columns are the only column we need to access. So example 3.1, analyzing whether people are more inclined to buy fresh fruit or candy depending on the day of the week. So select dim underscore date that weekday, comma dim underscore product that category, comma sum fact underscore sales that quantity, as quantity underscore sold. Next line from fact underscore sales. Next line join dim underscore date on fact underscore sales that date underscore key equal dim underscore date that date underscore key. Next line join dim underscore product on fact underscore sales that product underscore sk equal dim underscore product that product underscore sk. Next line where. Next line dim underscore date that year equal 3013, and next line dim underscore product that category in quote fresh fruit, comma quote candy. Next time group by. Next time dim underscore date that weekday, comma dim underscore product that category, semicolon. So how can we execute this query efficiently? In most OLTP database, storage is laid out in row-oriented fashion. All the values from one row of a table are stored next to each other. So remember, in the transaction database, the storage is laid out in a row-oriented fashion. All the values from one row of a table are stored next to each other. Document databases are similar. An entire document is typically stored as one contiguous sequence of bytes. You could see this in CSV example of figure 3.1. So the same thing with document databases. They also store contiguous sequence of bytes like this. So they are kind of like in one row as well, just like with OLTP or row-oriented database. In order to process a query like example 3.1, you may have index on fact underscore sales date underscore key and or fact underscore sales that product underscore sk that tells the storage engine where to find all the sales for a particular date or for a particular key. So remember, you would need a secondary index to process a query like that. Since we have a sales date on the column, the sales underscore product underscore sk, and the quantity, you would have most that tells the storage engine where to find all the sales for a particular date or for a particular product, because we're still dealing with the row oriented. But then a row oriented storage engine still need to load all of those rows, each consisting of over 100 attributes. So like, because it's an row oriented and though it is indexed to another table, it will need to load all the rows instead of just the needed column from disk into memory. So it will transfer from disk, load from disk to memory, and filter out those that don't meet the required conditions. That can take a long time. The idea behind column-oriented storage is simple. Don't store all the values from one row together, but store all the values from each column together instead. So, since you only need those three columns when accessing these large numbers of rows, you don't store that all values from one row together, or you don't append that document as an as appended like a one row. Instead, you store the values from each column together. If each column is stored in a separate file, a, a query only needs to read and parse those columns that are used in that query, which can save a lot of work. This principle is illustrated in figure 3.10. So if each of those columns are stored in a separate file, a query only needs to read and parse those columns. So if it's a separate file, you read and parse those columns that are used in that query, which can save a lot of work. This principle is illustrated in figure 3.10, storing relational data by column rather than by row. So as you can see here, date underscore key file contents 1402. 31455. So we store that per column rather than doing this previously. So column storage is easiest to understand in a relational data model, but it applies equally to non-relational data. For example, Parquet is a columnar storage format that supports a document data model based on Google's Dremel. So yeah, it's easier to understand in a relational database, but it doesn't erase the fact that it actually equally applied to a document storage like Firestore. The column-oriented storage layout relies on each column file containing the rows in the same order. Thus, if you need to reassemble sorry, the column-oriented storage layout relies on each column file containing the rows in the same order. So this rely that this row contain in the same position or order. That what makes it the query still possible in this column-oriented storage. Thus, if you need to reassemble an entire row, you can take the 23rd entry from each of the individual column files. So thus, if you need to reassemble an entire row, you can take the 23rd entry from each of the individual column files and put them together to form the 23rd row of the table. So if you want that 23rd table, you just check that in the column instead and put them together. So that's what's make it efficient. And then later we will discuss how do we actually compress that, that allow us to make those query efficient, and uh, we actually use how we subsequently use or transfer what we did with LSM3, which we create like an in-memory cache. So we will actually use that in analytics as well to make it more efficient, the data structure or the algorithms more efficient.